Okay. So I'm Niv Buchbinder. I'm a new faculty member here at the Open University. So I'm very happy to invite our next speaker, Irit Dinur. So Irit received her PhD in computer science from Tel Aviv University. She won the Nesiau Prize for her PhD dissertation on the hardness of approximating the minimum vertex cover and the closest vector in lattice. She is currently a professor in computer science at the Weizmann Institute of Science. Irit research is mainly in foundation of computer science and combinatorics, especially in probabilistically checkable proofs and the hardness of approximation. And today she will talk on the structure of NP-hard's 3-sat instances and Analogous question for locally testable codes. Okay, so thank you.
My microphone?
Microphone here. And laser pointer somewhere.
Okay. Okay, thanks, Niv, and good luck in your new position. טוב. אוקיי. רגע, מה הלייזר פוינטר אמרת? בבקשה. אוקיי. Yeah, okay, so if you saw in the program, I changed the abstract so you can compare what I thought was the real topic and then what I thought was the more sellable topic for the talk. So I kind of felt that maybe if I talk just about locally testable codes, it might seem a bit narrow for, like a theory day. So I'm going to spend half the time talking about my real motivation, which is like NP-hard 3-sat instances. Okay, so this is what I would like to talk about, but the only results that I have are about something else. Okay. Okay, so here is the PCP theorem says that basically it's a reduction. It's an algorithm that maps 3-sat instances, any 3-sat instance, into another one, such that if the instance was satisfiable, then the other one will also be satisfiable. And if it wasn't, if it's unsatisfiable, then the new one will be very far from satisfiable. You can only satisfy 7/8 of the clauses. Not all of them, not 99%, at most 7/8. And okay, this is a theorem we all know. And there are many parameters to the PCP theorem that have been well studied over the years. For example, the length. Just as an example, so if you map a 3-sat instance over n variables to another one over n prime variables, then you can ask, what's the length of the new instance? How much more, how large did the reduction cause it to be? And that's the length. The shorter it is, the better it is for various things, which I won't describe. Another parameter is the gap, which means, if first I had an instance where I didn't know if it's perfectly satisfiable or just unsatisfiable, the gap says, what's the fraction that I can guarantee? For example, here at 7/8, I can guarantee that, you can't find an assignment even better than 7/8. So it's something that's very important for approximability. There are many other parameters, the alphabet size, the number of queries, the type of constraint, the free bit complexity. There are many parameters, and people have been very interested in these things. Somewhat just for their own sake, somewhat because of applications for hardness of approximation. And I won't talk about all these things today. Rather, I want to talk about a different parameter or a different property of these reductions, which is the structure of the instance. Okay, so this is like a different kind of thing to look at. And I think it's very fascinating. There are some results that have been obtained along the years, but I don't think people were really focused on this as a topic, and I find it very interesting, so I'll try to explain why. So what do I mean by structure? It's very intuitive. So, I talked about 3-sat. I don't really care about 3-sat per se. Any CSP is fine. CSP is constraint satisfaction problem. So what is a constraint satisfaction problem? You have a bunch of variables, and you have a bunch of constraints that are local. So each constraint looks at, say, 3 variables or a constant number. F1 looks at x1, 2, and 5. F2 looks at x5, 1, and 15, and so on. You have a list of constraints. And the problem is, assign the variables with values to maximize the number of satisfied constraints. Okay, so what is the, so for example, right, max 3 sat is such a problem. Max 3 coloring, in max 3 coloring, each constraint is an edge in a graph. The variables are the vertices that can be assigned 3 different values, the colors. And the constraint just says, you know, on this edge, this color should be different from this color. The max 3 coloring problem would be to find a coloring that maximizes the number of edges that are not monochromatic. Okay, and there are many other examples. You know these things. So now if I have a CSP, I can always associate with it a constraint hypergraph. Right? What's going to be the constraint hypergraph? So it has vertices, which are just the variables. So you put a vertex for every variable. And then for every constraint that you have, if you have, say, a constraint over x1, x2, and x5, you'll put a hyperedge over x1, x2, and x5. Okay, so for each constraint, you'll have a hyperedge. Okay, so let's see a picture for this. So I have my variables x1 through x5 or x6. And then I have a function on x1, x2, x3. So I'll put a hyperedge here, right? And I'll put another hyperedge for x3, x4, and x5. Okay, so I put in all the hyperedges. I get a hypergraph. This hypergraph doesn't describe the entire instance because I also need to say what is the function on x1, x2, x3, right? So this just says that there is a constraint on these things, but you also need to specify what exactly the function is. So this hypergraph is part of the instance. Here's another example where the functions are over pairs of variables. Okay, so then it's not a hypergraph, but rather a graph. So actually, you know, we're not used to thinking of hypergraphs so much. So maybe for the rest of the talk, just keep in mind a graph, because it's maybe easier to think about. Okay, so for concreteness, you can think of the problem of maximum 3 coloring. Yeah. Okay, so when we talk about a constraint satisfaction problem, there's 2 kind of separate aspects, right? One is the structure, the graph structure, what I just described, this hypergraph. And the second thing is the constraint type, right? What kinds of FIs do we allow? Are they inequality functions? Are they CNFs? Are they linear equations? So these are like the constraint type. Okay, and often people think about CSPs and they classify them, but which constraint type you're talking about? And this has been well studied over the years. For different constraint types, we know different approximation behavior. For example, if the constraints are just linear equations, then Gaussian elimination will allow you to find the perfect solution if there is one. Okay, so this we know. If the constraints are 3CNF, then it's NP-hard to find the perfect solution. And in fact, Johan Hastad proved that this is a very celebrated result, that it's NP-hard to do anything better than random. So a random assignment will get you so much, 7/8. You cannot do better than random unless P is equal to NP. And there are many other constraint satisfaction problems you can think about, and for each one we have some results. And in fact, we don't know the entire thing, but there is the famous unique gains conjecture that Subhash Kot made maybe 9 years ago. And this conjecture, if it's true, it has a very strong implication. It says that every CSP that you can think about, we already know what's the perfect optimal solution for it. This is a wonderful theorem proved by Prasad Raghavendra. He proved that you take a CSP, a semi-definite program, which is generic in a way, and it's like what you can probably write. And it turns out that this semi-definite program will give you some approximation factor, and that's the best factor that you can hope for, assuming the unique gains conjecture is true. Okay, so this factor will be different for different types of CSP. When I say types of CSP, I mean the constraint type. So if it's a max-cut CSP, you will get some factor that is the Gomez-Williamson factor. If it's a 3-sat, you will get Hastad's result back. For each CSP, for each different type of constraint, you will get some factor depending on the integrality gap of the SDP. And this is the best result, assuming that this conjecture holds. Okay, now we don't know if the conjecture holds, and in recent years, we hear more and more people that kind of doubt this conjecture. So I'm not going to talk about it too much. Just to say that this kind of line of research of understanding how the constraint type affects the approximability has been quite well studied, although there's still a lot to do. One very, very interesting thing, I find it very interesting, is the following connection that was discovered maybe a year or two ago, that if you want to prove the unique gains conjecture, one thing you can do is prove another conjecture, which is called small set expansion. This is a conjecture by Raghavendra and Steurer. And the interesting thing pertaining for today's talk is that the small set expansion conjecture is not about a CSP in the way I described it. It's just about the structure of graphs. It says something about the expansion of graphs. Particularly, it just says if you have a graph, it's hard to decide if there is a small set that mostly does not expand or if every small set expands. Okay, so it's hard to decide between these two things. This conjecture implies the unique gains conjecture. So it shows already some kind of connection, or at least one-way implication, between structure and in this line of research. So even in this line of research, you are led to understanding that the structure of the CSP and the structure of the graph is very important. It's very important to understand what the structure is. Okay, so now let me tell you additional reasons why I think understanding the structure is interesting. Okay, so the first reason is just repeating the same sentence again. I just think that it's interesting, right? So I find just this question of, you have a max CSP problem. You want to know what do these graphs look like on which the problem is hard. Certainly if the graph is like a path or something trivial like this, the problem will not be hard. So maybe we can say something meaningful about which graph structures are hard. And why do I talk about hard to approximate? The reason is because when I talk about graph structure, I'm interested in robust notions of structure, something that doesn't care about a change in maybe an epsilon fraction of the edges or something like that. And these things kind of go together with the hardness of approximation, because if something is only hard in its exact version, then changing epsilon fraction of the edges ruins everything. So these two things are naturally coupled. So one perspective which this question can be studied is which kinds of properties do graphs of hard instances. Okay, so I have a hard instance and I look at its graph or hypergraph, and I'd like to know if there are some properties that every hard graph possesses. Right? Maybe you can tell me, every graph on which this and this problem is hard must at least, be something. For example, it must have a high tree width, right? So this is actually a theorem, because we know that when a graph has low tree width, the problem is solvable in polynomial time. Okay? So, going along this direction, maybe we can find more properties that actually even characterize when an instance is hard or not. Another similarly looking property is expansion. Is it true that whenever whenever a hard instance has a certain graph, this graph should be an expander? So this is a question we will go back to. It will be the topic of this talk, actually. So I'll get back to it in a minute, but this is a different kind of question. This question is, maybe we can find specific instances on which max CSP is hard, some very beautiful graphs. And you can say, on this graph, it's already hard. You don't have to worry about all kinds of graphs. Here's a very nicely described graph, and already here it's hard. So that would be very nice, to find max CSP to be hard on specific graphs. So here are some examples on which maybe I can dream that max CSP is hard. So I don't know if it can be hard on the n by n grid. It looks actually unlikely. Other candidates might be the Hamming cube, or maybe just some Cayley graph of a group, right? So some graph with nice symmetry properties. It would be great to prove that 3-sat is hard on such a graph. even greater to prove that no matter which graph you give me, as long as it's an expander, 3-sat will be hard on such a graph. So we know how to prove similar things, but much weaker. I'll describe it next. Yeah, okay. Okay, so here are some things that are known. Probably more things are known, but I've just kind of collected these things out of memory. So already Polishuk and Spielman in '95, they wanted to prove some theorems about PCPs, and so they took their PCP instance and they forced it to be placed on a very nice graph called the De Bruijn graph. And the way they did it is they took every constraint, every edge in the original arbitrary instance, and then they just routed it. Okay, so they, instead of putting an edge between U and V, they said, well, I can't use this edge. It's not in the De Bruijn graph. I must use the edges of the De Bruijn graph to find the path from U to V. Okay, and it turns out that the De Bruijn graph was not just arbitrarily chosen. It was chosen because you can do very nice routing using it, and this gave them some power because they could then utilize the power of the structure of the De Bruijn graph. And we actually, with the Or-Meir, in a much later work, we reused their idea to create a PCP instance with very special structure that we call the linear structure, and this allowed us to prove some de-randomized parallel repetition theorem. I'm not going to get into it at all, just to say that when you do that, we also did this routing idea of routing constraints between U and V along the path of the De Bruijn graph. And how do you do this routing? You start out with your vertex U, and then you just enforce equality constraints along the path, so that U has to be equal to U prime, equal to U double prime. And at the last edge, between U T primes and V, you put the original constraint. And so any assignment to this whole thing that must falsify the original constraint must falsify at least one of the edges. So if your path was of length t, you lost some factor of t in this reduction, because now you can satisfy almost all the edges except for one. And in fact, when you do this routing thing, the length of the path is going to be log n. And this is why, instead of getting a constant here, like 0.99, we got 1 minus 1 over log n, polylog n. Okay? And this kind of routing approach inherently loses this log n, except, in PCPs, since everything is approximate, you can really try to route only 90% of your pairs. And this might give you more power. So, I'm not an expert at all about routing, so I feel this is a question maybe, someone in the audience knows more about than I do. And this is actually very motivated. If someone is able to do this in time that is with a parameter that's 0.99 rather than 1 over this, this will give a significantly simpler proof to one of the strong PCP theorems that currently have a quite difficult proof. So this would be one kind of shortcut around that. Okay. Okay, so what this kind of result demonstrates is that if you have a structured instance, then further reductions can use them somehow. So it's one reason to want structure. And in fact, this was also used by Uri Feige in a very beautiful paper of his tying a random 3-sat to a hardness of approximation. He assumed that refuting random 3-sat is hard, or he didn't assume, he hypothesized that it's hard. And from this hypothesis, he showed how to get rather easily several results about hardness of approximation of problems that, for example, densest subgraph. These are problems that until today we don't know of any other way to prove that they are hard. And why did assuming that random 3-sat is hard help him? Because the structure of random instances, random instances behave in a certain way, and it's very convenient for the reduction to rely on that. So it's the same kind of idea in both of these works. In a different kind of work, a recent work of Uri and the student Shlomi Joseph, they showed that there is one graph, or hypergraph, for 3-sat, such that, say, for instances of length n, there is one graph on which 3-sat is hard. So all you need to change is the polarity, say, of the variables. And you don't have to worry about all kinds of graphs. There's one graph on which this thing is hard. Of course, then one wonders how does this graph look like? Can you make it be the Hamming cube? Can you make it be something more, manageable? So there's still plenty of things to understand there. On the reverse side, there is this work by Aurora et al. That showed that actually for unique games, which is a kind of constraint satisfaction, if the graph is an expander, then this problem is easy. So here you show a certain graph on which the problem is hard. They showed that whenever the graph is expanding, unique games is easy. Actually, this is not believed to be true when the CSP is not unique games. It's probably going to be hard, but who knows? Okay. So what are some of the motivations we've seen? First of all, understanding structure is relevant to approximation problems where structure is inherent. For example, if you want to understand how hard it is to find the expansion of a graph, this is a question about a structure of a graph. So naturally, the structure is there. But also, as I showed, understanding the structure of hard instances will be useful for reductions to other problems, probably. On the flip side, you can say, well, maybe you can show that whenever the graph has a certain structure, algorithms can use it. Okay, so a structure can be used to, give the algorithm more power. And the flip side of that is that, you want to understand when this doesn't happen. So, which kinds of structures exist in the hard instances. Okay, so these are the main themes of this line of work. And now I want to go to a specific question, which I mentioned before. And this is, if you have a graph of a hard instance, is it necessarily an expander? Okay, so suppose you have a reduction from some NP-hard problem, I don't know, to max 3 coloring. Right? And you want to know whether the graph that you came up with, this reduction gave you a graph, is this graph an expander? Right? So what do you think? The reason I think it should be an expander is because, if this graph is not well connected, if it's made of different parts, then whatever algorithm I can think about for 3 coloring, I can apply it separately to each piece, right? So I can do a divide and conquer thing. I'll find some way to partition the graph so that I don't lose many edges, and then I'll work separately on 2 sides and continue in this way. So you would expect the graph not to have such a structure, right? Because we believe that NP is different from P. Suppose we believe that. But on the other hand, here is a very trivial reason why the graph, you can't expect it to be an expander, right? If you have a graph that's hard, on which it's hard to decide if it's 3-colorable or far from 3-colorable, then just think of placing 2 copies of this graph side by side, just on double the number of vertices, okay? Then how hard is it to maximally color a maximal number of edges properly? It's just as hard. I mean, if there's a way to color the original graph perfectly, you can also do it now. And if when you color the original graph, you always leave 1% of edges bad, it's the same 1% that's going to be left bad when you color, the graph twice on 2 different copies, right? So you see, on the other hand, this graph of 2 copies side by side is certainly not an expander, right? There's no edges going in the middle. Okay? So, I mean, what does this tell us? It looks like a very artificial problem, right? Something that, by something that by, the correct definition or, something should be found to work around this problem. But, okay, I'm not sure how to do it, so that's where the enter the locally testable codes. Okay, so we have this parallel universe to PCPs that is called the LTCs, locally testable codes. And in this world of locally testable codes, many things that are maybe harder for PCPs can be, formulated more nicely, more elegantly. And this is going to be an example for that, or at least that's the way I think of it. So we'll get back to the problem of this 2 copies of G, but let me first describe locally testable codes. Okay, so I'm going to now define a locally testable code, not in the way we're used to it. So here it is. A locally testable code, LTC, is just given by a constraint hypergraph. So the same thing we had before, a bunch of vertices, hyperedges on them, and for every hyperedge there is some constraint. Okay, and then the code is just defined to be the set of all assignments to the vertices. So say the vertices are just the numbers 1 to n. Okay, so just assign the vertices with values in a way that satisfies all constraints. Okay, so for every satisfiable assignment, that's a code word. And the set of all words in the code is just the set of all satisfying assignments to this constraint graph. Okay, so that's going to be our definition for LTCs. And of course, that's not the entire definition yet, because there's going to be some requirements. Not every graph, when you look at this set of satisfying assignments to the graph, gives you an LTC. So I'll shortly state another 2 properties that I require. But before, I think I have a picture, right? Yeah, okay. So here's a picture of an LTC. So I have my vertices, the numbers 1 through 6. I have a bunch of hyperedges, and here are the constraints. In this case, they're all linear constraints. And it's just the set of all strings of 6 bits such that they obey these constraints. Those strings are the code words. Okay, so I thought I would have time to complete the list, but okay, I did not. Okay, so what are the 2 properties required from the constraint graph or from the code to make this a locally testable code? So the first is distance. You require that the set of satisfying assignments, which I denoted C of G, the code defined by the graph G, this is a set of strings. I require that it has good distance in the sense of error correcting code, right? That every 2 strings differ on such and such number of coordinates. Okay, omega n. So it should be some linear number of coordinates. Okay, that's one requirement. And the second requirement is a requirement of robustness. It says the following. It says that whenever you have an assignment to the vertices, so this is like a potential code word, you have an assignment to the vertices that falsifies few of the constraints, okay, no more than an epsilon fraction of the constraints, then there is a way to correct it. Okay, then it means that this assignment must be delta close in Hamming distance, so meaning you need to flip at most delta fraction of the coordinates of this assignment to make it into a valid code word in C. Okay, so again, if you have some assignment that's already pretty good, okay, it satisfies 99% of the clauses, then it means you can flip some 2% of the bits in the assignment and make it into a perfect assignment. Note that this certainly is not a property of an arbitrary code. For an arbitrary code, there can be words that are that satisfy almost all of the constraints and yet are very far from the code. Okay, so this is definitely a requirement that's non-trivial. Actually, it's non-trivial when the code has good distance. Okay, so robustness is interesting when the code has good distance. If, for example, the code contains all words, then of course this requirement is trivial, right? You're always delta away from a code word. So only when the code words are very far apart, guaranteeing that you're delta close to something makes sense or is interesting. Okay, in fact, it's not only that it makes it interesting, these 2 requirements are somewhat in tension with one another. All right, okay, so since I'll talk about locally testable codes for the rest of the talk, I put the classical definition up here just to go over it one more time. So what is an LTC? It's just a subset of strings, just an error correcting code with constant relative distance. So this is just an error correcting code. And plus this extra thing that you have a constraint graph on the n vertices that has the 2 properties. One, it defines the code, meaning a string is in C in the set of code words, if and only if all of the constraints accept this word. And this is the robustness property. Whenever a word is far from the code, it must cause many of the constraints to reject. So this is the contrapositive of what I said before. It means that if not epsilon of the constraints reject, but fewer, it must mean that the word is close to the code. Okay, so this is a locally testable code once more. Okay, now let's talk just a couple of words about the connection between locally testable codes and more general error correcting codes. Okay, so the first thing that I've already mentioned is that most error correcting codes are not locally testable at all. For example, an error correcting code can be given by just taking a random linear subspace. Okay, a random matrix will give you a good code in terms of distance, but it's not only that it's not locally testable, there is not even one single constraint that you can say about that code. All of the constraints that say, for example, x1 plus x2 plus x3 equals 0, they must use a linear number of bits to have some meaningful equation. Okay, so it's really far from being locally testable. It doesn't even have local constraints. Okay, and then you can look at LDPC codes, which are exactly codes that do have local constraints that are defined by low density parity check. It's exactly, parity check is a check that says x1 plus x2 plus x3 equals 0. And low density means there's only few variables in this equation. Okay, so even an LDPC code, say a random one, where you just randomly take a matrix that has low density on every row, defines a code that's, it's far from being locally testable. You can show that there are words in this outside of this code that are far from the code, but they satisfy all constraints except for one, for example. So it's very, very far from being locally testable. Okay. So now before I state the theorem about LTCs, I want to say, why suddenly I broke from the world of CSPs or PCPs to LTCs? What's the connection between these two objects? Okay, so both are defined through constraint graphs, right? So that's kind of a similarity. In both cases, there is some notion of robustness going on. In LTCs, it's based on the distance. You know that when you satisfy almost all constraints, you must be close to a valid code word. For CSP, you know that when you satisfy almost all of the constraints, you must be close to a satisfying assignment. Or in other words, it's not exactly true. The more correct way to say it is that your instance must be a satisfiable instance. The main difference between the two is that LTCs are a combinatorial object. There's nothing computational about it, no mention of NP, no mention of any kind of computation, which makes it makes it simpler to understand, simpler to define. You can define it to a mathematical audience. They don't look at you kind of with strange looks. And whereas PCPs are computational, so you must all the time carry this notion of NP hardness, and it's harder to deal with. And also there is this empirical thing that similar techniques are being used to construct both objects, to analyze both objects. So it just seems that LTCs are a good testing ground. If you want to prove something about PCPs, you might want to start proving it about LTCs and kind of understand what's going on. Okay, so this is what we're going to do. כמה זמן נשאר לנו? 10, okay. So it's just enough time. So this is what we're going to do. Remember, I wanted to understand this notion that a constraint graph of a hard CSP, a CSP in which it's hard to decide, say, if 3-sat is satisfiable or far from satisfiable, is it true that such a constraint graph must have expanding structure? And our problem, or my problem was, that it's blatantly false, right? That if G is a hard instance, then you can just construct the graph GG, right, which is just placing two copies of G one next to the other. And this graph is not even connected, right? So it's certainly not an expander. Right, so this is the picture. I had G, now I have two copies of G. There aren't any edges here, and yet it's just as hard in terms of 3-sat, for example. Okay, so how does it look in terms of LTCs? So the same picture stays, but now I think of G as a constraint graph that defines an LTC. Remember, the LTC is just the set of all satisfying assignments to these constraints. Okay, so if G is an LTC, GG is actually also an LTC. What are the code words of GG? It's all words of the form x, y, where x and y are each words in the previous code, right? Because you have to put some kind of assignment here that satisfies the constraint, and another kind of assignment here. So if words here have length n, words here have length 2n. Okay. And what does the code look like? You can really write it as C times C, right? It's just a Cartesian product of the code that you had here. Very, very simple thing. But now notice that there is a change in parameters that is actually what we're going to leverage. What is the distance of this new code? So if before two code words differed in some d coordinates, now two code words here can be of the form x, y. That's one code word. And x prime, y prime is the other code word. But x and x prime can be equal. And only y and y prime will differ. So there are pairs of code words here that differ, again, on exactly d coordinates. Okay? So what does that mean? That the relative distance is now half what it was before. Right? If it was d over n before, now it's d over 2n. Because the length of the code words double. Okay. So that will help us. And here is how. In general, the GG example can be generalized to placing t different constraint graphs of LTCs side by side. And the new code that you've generated is just the set of strings of length n1 plus n2 all the way to nt. Strings such that the first n1 bits are a code word here, the second set of bits are a code word here, and so on. And, oops. And in this case, the resulting code will be just a Cartesian product of the t, primitive codes here. And notice that the distance, the resulting relative distance of the entire new code is smaller. Because, again, because of the same reason, the distance is at most 1 over t times the best distance. So anyway, 1 over 2t. Yeah. Now, notice that if for LTCs we require the distance to be constant, the relative distance to be constant, this means that this cannot go on for a long time, right? Once t becomes too large, the relative distance drops beneath my lower bound. So it means that such a construction, the number of kind of separate copies will be bounded by something that relates to the distance. Okay, and this is what we leverage, right? So here is our main theorem with D-Kaufman. It's a very simple theorem, but I find it's just the right way to state, and you see that the proof is just one slide. So I have an LTC, a code C, that's defined by some constraint graph. So let's think of the following thing. Suppose it's defined by a constraint hypergraph. You can always look at the skeleton of the hypergraph, where you replace every hyperedge by a click. Or in other words, you connect two vertices by an edge if there is some hyperedge that contains both of them. Okay? So let's think of this as the graph. And the claim is that the set of vertices can now be partitioned into t parts. Okay, so this is for any LTC. It's not the one that I constructed before. Now we're saying a general statement. Any LTC there's a way to partition the vertex set such that if you define the code CI to be just the code restricted to this VI, meaning you look at all the strings in the code, and you just look at the set of coordinates corresponding to VI. Okay, and you just project and look at all the possible values there. Okay, so that's going to be CI. Then the code is actually almost equal to the Cartesian product of C1 times C2 and so on times CT. Okay, so for example, if t is equal to 2, okay, then it means that you can partition the vertex set into two parts such that the code is essentially a Cartesian product of two codes, just like in the example we analyzed before. Okay, and the reason for this almost is because we will have edges. It won't be two separate copies. There will be edges, and so it will be an almost thing. Okay, and such that the graphs on each VI, so you partition the vertex set into these VIs, on each VI, the graph is already going to be an expander, right? If, like I wanted. So this answers my problem that I had before. I said I have G, and then I duplicated, and now it's no longer an expander. So the theorem says, well, that's the only thing you could have done. So, you know, your graph really decomposes into these bunch of separate things, and each one of them is really an expander. And as I said, the number of copies T is related to the relative distance, so it's just a constant. And the expansion, how well G expands, relates to the parameters of the LTC, and let's not get into that. Okay, so right, so this is my last slide before the summary slide. And it's a proof, and you'll see it's almost like, you know, it's like a homework. Okay. So I have a code, and it comes with a constraint graph, the skeleton thing that I said. So instead of a hypergraph, we look at the graph. If this graph has no sparse cuts, it's already an expander, right? So we're done, okay? I didn't define what expanders are, right? I should have done that. So who doesn't know what an expander is? Okay, so why didn't you ask me to begin with? Okay, so now is a good time to define. An expander is a graph where from every set, a lot of edges go out. Okay, so an expander is exactly a graph that doesn't have a sparse cut. A sparse cut is something where you cut the graph into two parts and few edges go in between. In an expander, from every set, many of the edges, not all of the edges will stay inside, but many of them will go out. Okay, so I apologize for that. Okay, so if G doesn't have a sparse cut, by definition, it's an expander, and I'm done. Otherwise, let's look at some sparse cut. Okay, so AB is a sparse cut, meaning I take the vertex set and I cut it into A and B. Okay, and there's few edges going in between. And here's my picture. And now let's look at the codes. I mean, what else can I do, right? So I look at the code C restricted to A. So what is this again? C is a code. It's just a set of strings which are viewed as assignment over the vertices of the graph. So each string is an assignment over the vertices. And you can take each string and just look at what it looks like on A, right? So you get a shorter string. And C1 will be the set of all strings you obtain by taking a code word and restricting it to A, and similarly to B. Now notice that for usual codes, it won't be the case that when you restrict the set of code words to the first half of a coordinate and to the second half, then for any combination of two of them, you will get a valid code word. It usually will not be the case. But the claim is that if there is a sparse cut between A and B, then this will be the case. We claim that indeed C1 times C2 is almost equal to C. And this notion of almost equal is, I think, what you would expect. It says that for every word here, there is a word in C that's very, very close to it in Hamming distance. And of course, containment this way is obvious. C, every word here is inside C1 times C2. Okay, and here is, how to prove it, right? So think of what do you need to prove such an equality? You need to prove that whenever you have a word in C1 times C2, something happens. So what is a word in C1 times C2? A word in C1 is some word in Cx where you chopped off the B part and you're just left with the A part. Okay, so this is here, it's this XA. Okay, it's a word that was in C where you only look at the A part. Okay, and then you have another word in C, Y, that you only look at its B part. Okay, and so a general word in C1 times C2 is just a word that looks like this, X on the A part, and next to it, Y on the B part. Okay, so this is a generic word in C1 times C2. Okay, and I call it a hybrid word because it's built up of two different words. Right? And then what can you say about this hybrid word? Okay, if it's already close to a word in C, then I'm done, because that's what I want to prove. I want to prove that every word here is very close to a word in C. Okay, so if it's close to a word in C, I'm happy. If it's far from a word in C, okay, which would be the case in a general code, it might be that a hybrid word of two words where you arbitrarily put them, it would be far from a word in the code. But here, if a word is far from the code, then the LTC guarantees me something, right? Guarantees that many of the constraints must reject. Okay? If you're far from the code, many of the constraints must reject. Okay, so who's going to reject this word? A constraint that's fully contained in A cannot reject this word because it doesn't, this constraint doesn't know that the word is X, A, Y, B. It thinks that the word is X, right? So it certainly won't reject. Similarly, a constraint inside B will think that the word is Y, so it also won't reject. The only constraints that can reject this word are constraints that cross the cut, okay? And by assumption, this was a sparse cut. Not many constraints cross this cut. So only few constraints reject. What does it mean that few constraints reject in an LTC? It means that the word is correctable. You can change it only a little bit and make it into a word perfectly in C. And so this proves that XAYB is close to a word in C, and that's the proof. Okay, so this just says what I just said. Finally, okay, so we did it just cutting in two. Now you look at the graph induced on A, and you ask yourself again, is this an expander, yes or no? If it's not an expander, you repeat the process again. And similarly here. And we know, because of this distance argument, that this cannot go on for too long. Yeah, so that's the proof. And you see how, it's very easy, it's simple. There's nothing really to it. Once you just need to tie it correctly to the definition. And somehow, when you look at CSPs, you don't have the distance to help you. And it makes things, it's possible to say something, but it's much less elegant, right? So to summarize, okay, so we saw this basic structure theorem about the LTCs. And I look forward to a nice extension to CSP. So there's some things that can be said, but you want them to be more crisp. Okay, I tried to describe some questions about the structure. I think there are many interesting questions, and there's much to do. Not very much has been studied in these questions, so please do. And just to mention a related question about structure that recently we had worked with Tali, and in parallel, Eli Ben-Sasson and Michael Widerman also proved that something else about the structure of LTCs, that these graphs cannot be dense. The constraint graph cannot be dense. It cannot have too many constraints without really harming the rate. So just to say that, work on structure is going on LTCs kind of separately, and maybe this too can be brought back to CSPs. Yeah, I don't know. Okay, that's it. Everything is clear.